Uh, Welcome to this course and welcome to the graduate school. I think this may be one of your first lectures, right? Uh, so I'm going to teach the first introduction that you are going to get to the field of astronomy and astrophysics. Uh, Therefore, the nature of this course is going to be very different from the other core physics courses that you are taking, as well as with respect to the other astronomy courses that you will take in the future. And that is because this is like an overview course. The goal here is just to get you familiarized with the subject, get you used to the jargon and so on. It is not to go into depth in anything. So it's going to be a very wide course, but not a very deep course. And that has implications to many different things, as we shall see. Okay. So there is a web page that I have constructed. So if you want to make notes, just write down the URL of this. So what I will be doing is the PDF file for each lecture will be put up on the website immediately after the lecture. And so you don't have to bother writing down anything that's already on the screen, but you can make notes from what I am talking, because I'm not going to put up the videos. I'm actually recording this over Zoom, but I will not put up all the lectures till the course is over, because I want you to attend the class and pay attention here rather than just trying to watch via Zoom. But you will be able to access the slides. And my email address is given over there. Please feel free to reach out to me anytime over email. If you need to meet me, then you will need to make an appointment, because I have so many meetings through the day that I'm often not in the office. I'm somewhere around. Okay. So this course will be in classroom mode. Lectures will be live here in the NCRA lecture hall. You already have the schedule. There will be a total of 14 lectures over 7 weeks. Okay. And in case there is a holiday on one of our scheduled days, I'll try to reschedule the lecture during the same week so as to finish on time. I think that's important, because what tends to happen towards the end is that lectures are going on, exams have started, assignments are due. I mean, you guys will feel a lot of pressure. So to relieve the pressure, I'll make sure that I finish my lectures well before the exams start. Okay, so I have a little sheet of paper here where I want you to write your name, institution, and email address. This is just so that I can send you email in case there is any change of schedule and so on. So please, that sheet, please circulate it around and write your name on it. Okay. So let's do one round of introductions here. So let me begin by introducing myself. So my name is Yogesh Wadadekar. I was a PhD student at IUCAA many decades ago now, not many years ago. I did my PhD under the supervision of Ajit Kembhavi. And for the last 30 years or so, I've been working on galaxies. So I study galaxies, but in galaxies in various aspects, both what are called normal galaxies as well as what are called active galaxies. I finished my PhD in the year 2000. After that, I was a postdoc at the Institut d'Astrophysique de Paris, that's in Paris in France, for a year and a half. And then for 3.5 years, I was at the Space Telescope Science Institute in Baltimore. This is the institution which operates the Hubble Space Telescope, and now more recently, the James Webb Space Telescope also. Then after that, for about a year and a half again, I was at Princeton University at the Department of Astrophysical Sciences, where I worked on basically the Sloan Digital Sky Survey, which is one of the big surveys, optical sky surveys of recent times. And then after that, in 2007, I returned here. So I've been here for about 17 years now. I have taught extensively over the last 15, 16 years. I'm teaching this course only for the second time, but other courses like galaxies and astronomical techniques and so on, I have taught several times. So that's my long introduction. Nowadays, I continue my research work on galaxies, but I'm also heavily involved in software development work that we are doing for a new next generation radio telescope called the Square Kilometer Array. So India is doing a lot of work in this area, and I'm heavily involved with that. So all of you don't have to give such a long introduction, but just we'll go around the room. Just tell me your name, okay? And tell me whether where you did your previous degree from, and whether you're from IUCAA or NCRA, because even the NCRA people I've not met most of them yet. So just introduce yourself, and this is important that I sort of record your names in my head. And for the next few days, I may just ask you for your name again and again, and I'll tell you why in a minute. So yeah, why don't you start?
I'm Hardik Nirgin. I'm from the Institute of Guwahati, Assam.
Okay.
And I completed my master's in Ferguson College.
Okay. Okay.
And I got into NCRA through BSR. Last year I was there for 2 weeks.
Okay. Who did you do your project with?
Dr. Jainta Bhatt.
Okay.
On FRB system.
Okay. Good. So you are it.
I'm Barun. I did my master's from XRI. Yes. And I got into GS.
Okay.
I'm from West Bengal. I completed my from IIT Kharagpur.
You are in NCRA. Okay. Yeah. Yeah. Huh. Okay. So 3 of them are NCRA, 2 of you are IUCAA. Yeah. Good.
Yeah, Swami.
Huh. Okay. You are in.
I'm Subhan Sir.
Sorry, Shubham.
Subhan Sir.
Yeah.
I'm from Uttarakhand. And I took my from IIT.
Okay.
I got into IUCAA.
Okay.
And
INAT. Okay. Yes. From last year, and now you are. Where did you do your bachelor's from? Oh. Yeah. Through the yes. Okay.
My name is Deepak Patel. I'm from Uttarakhand. I did my master's from University. I'm a Patel.
Okay. Right. So we have how many people from NCRA? Only 3? 4 of you, Jatin. Yeah. And 1, 2, 3, 4, 5, 6. All of you are at IUCAA. There is no one. I was told that there may be some students from the university who may be joining, just auditing this course. But it seems like none of you are in that category, at least at the moment. But maybe they'll join later. Okay. So please fill out the names and addresses so that happens. Okay. So this is why I wanted to get introduced to all of you. Okay. So we are going to have evaluation in the form of 2 exams, 25% weightage for a midterm written exam, and 50% weightage for a end-term written exam. That's 75%. But I'm reserving 25% for class participation. Okay. And this involves both asking and answering questions. So I would like all of you to be, because for many of you, all the topics will be very new. You wouldn't know much about it. So please feel free to interrupt me at any time and ask. Okay. Because sometimes I may just not realize that a particular piece of information or jargon is not familiar to you and just go hurriedly over it. So please stop and ask me questions. And of course, where I have questions sprinkled throughout the talks. So I will stop and I will ask you to answer the questions. So please try to answer those questions because that is going to gain you eventually 25% of your marks. Okay. So normally I don't like to give exams. Okay. But recent advances in generative AI technologies have made assignments impractical. Okay. Because I put through some of my previous assignments through the latest generations of these AI technologies. And even if they don't give you the full answer, they give you so many hints in the right direction that a reasonably smart person can in 5 or 10 minutes figure out or even the most difficult question. So let's not go that way. Okay? There are big discussions going on at NCRA and presumably at IUCAA also about what should be allowed and what should not be allowed. But right now we are just by doing a classroom exam, we are avoiding that controversy for the moment, but things may change. I also wanted to state that you people may be the last batch that does this graduate school. Okay, the graduate school is being reformed for two reasons. One, because it's 25. The syllabus and the course organization that we have today is 25 years old. So we obviously need some kind of a revamp. But also there are instructions coming in from the UGC and higher bodies like that we have to sort of restructure our courses to make it sort of compliant with the new education policy and so on. So there is a big exercise going on. So we were thinking of implementing that new organized course organization this year, but there wasn't enough time. So it's not going to happen this year. But next year onwards, the next batch onwards, they will see a completely different course structure. So of course, courses like this will always be there, but the exact arrangement will all change around. Okay, so the nature of the midterm and end term exam, this will be a closed book exam, okay, with a number of short questions to test your conceptual understanding. Okay, the duration will be 1 hour for the midterm and about 2 hours for the end term. So I don't want to give very long exams and so on. So this is because this course is just orientation to the basic concepts of astronomy and astrophysics. We will not have very long questions and very detailed answers and so on. They will be all short questions in the exam. Midterm, as expected, we will do about a month from now, and end term will be about 2 months from now. So here's the official syllabus. Earth, solar system, the sun as a star, stellar structure and evolution, the HR diagram, color, magnitude, spectral classification, then the end states of stars, white dwarfs, neutron stars, and black holes, binary stars, the interstellar medium or ISM, structure of the Milky Way, stellar populations and galactic structure, cosmology, brief description of galaxy morphology and evolution, active galaxies and clusters of galaxies. Okay, so as you might imagine, this is quite a vast thing, and we won't be able to go in depth in any of the topics because, I mean, for example, I have taught 21 lecture course on galaxies, mainly on galaxy morphology and evolution. I have taught a 14 lecture course on active galaxies. So obviously, I cannot cover in a 14 lecture course that covers all of astrophysics in any detail. Okay. I will place greater emphasis on topics that are actively researched in our two institutions. So for example, the Earth and solar system is something that is not very actively researched here. So I will not place too much emphasis on that. I may just skim over it. On the other hand, many recent areas which are active areas of research at our two institutions, like, for example, gravitational waves, fast radio bursts. Extrasolar planets is not very actively researched here, but it is a very active field of research worldwide. So I will cover that also. So in addition to many of these topics, one will have to at least touch upon some of these topics which are not covered in the syllabus. This course has linkages to all your 7 other astronomy courses. So there are like 7 core astronomy courses that you will take over the next year. And here the goal is to give you a broad overview of all the subfields of modern astronomy and introduce the jargon and the methodology of the subject. Okay, so we will try to do that. The jargon, at least, I think you will get. Methodology is harder because it requires you to spend more time thinking about what's going on. We may not have that much time, but let's see how much we can achieve. Textbooks. So there isn't any one textbook that is sufficiently comprehensive and current for our purposes. There are textbooks which are sort of undergraduate level textbooks. So in the United States, there are many programs where you can do a BS in astronomy. Okay. And for such courses, they use some very, very broad textbooks. They'll have titles like The Universe or something like that. And they will cover all the topics that we need to cover. But they're very simplistic in many ways. They don't go into depth at all. So we don't want to do that. That's why I'm not recommending any of those textbooks. But what I will put up on the web page is a list of books that I am referring to, which you will also find useful. And this is likely to grow as the course progresses because new textbooks keep coming out. Both IUCAA and NCRA have access to what is called Springer Link. This is from one of the leading publishers. You can access all their astronomy textbooks online. So I will use mostly those because some of the other textbooks, so Cambridge University Press is the other major publisher. Both our libraries have those textbooks, but often there's only a single copy and it's hard to get and so on. So I'll try to avoid those. And of course, this will only be required if you want to go into depth in some topic. I'm going to give you an overview anyway. And some of the slides will cite papers and which you are encouraged to read to know more. So astronomy is a very active field of research. About 35,000 refereed papers are published every year. So that's approximately 100 new papers a day. So obviously, one can't keep up, even if you are keeping up with a subfield, you can't keep up with the literature. So you have to read selectively. So I will point you only to sort of seminal articles or review articles in a particular field where you can get the gist of it all in one go. Okay. So are there any questions about the course content and organization? No? Yeah. So astronomy is the oldest science. So if you ask yourself, which astronomical discoveries occurred the earliest and why? Okay. So would you like to think about it? What were the first things that people discovered about the sky? They discovered planets. Even before that, they discovered, of course, the daily pattern of the sun and so on. They discovered the seasons. They discovered that at certain times of the year, the sun is not up for very long. And at certain other times, it's up in the sky for a very long time. They also discovered which way the sky moves. So everything rises in the east and sets in the west. So they notice those patterns. And soon after that, they discovered the motion of the planets. Okay. Why did they discover these? I mean, were these useful in any way? For example, the seasons, was there any use for agriculture? Yes. So, for example, in Egypt, there is something known as the heliacal rising of Sirius. So, if you see the star Sirius in the morning sky, that was the indicator that the Nile is about to flood. And they use that to plan their agricultural activities. So, and of course, in other countries of the world, there were patterns when, so for example, in our system, there is when the sun is in a particular nakshatra, then the rains will start, and then winter will start at some other time, and so on. So the other astronomical discoveries were related to the fact that the same stars are not seen at the same place at the same time every night. They keep moving, okay? And that had a pattern. The whole pattern seemed to repeat every year, the solar year. So the concept of the solar year and the concept of the seasons, everything was measured. And the earliest astronomers were also the first calendar makers. So people had various calendars across the world. We will see some of them later on in this course. But calendar making was also a major activity in all the ancient civilizations. But much of what we will study will not be this historical astronomy. We will study what we call modern astronomy. And that really began with the invention of the telescope around 1610. And Galileo was the first person to turn a telescope up towards the night sky. And he made a number of discoveries. You may be familiar with some of them. But really, that is a turning point. Philosophically speaking, the turning point came with the work of Copernicus, which showed that the sun was at the center of the solar system. That book was written 150 years before Galileo, but it did not receive that much prominence and attention until the time of Galileo, and where he was able to use the telescope to actually observationally verify some of the ideas that followed from the Copernican model. So philosophically, it started in 1453, but more practically, it started in 1610. And that thing, telescope, is crucial. It is the most crucial instrument. Just like a stethoscope is the first thing a doctor will go for. Similarly, the telescope is the first thing that an astronomer needs. And over the years, over the centuries, the telescope has evolved. Okay. Originally, you only had optical telescopes, but now you have X-ray telescopes and radio telescopes and gamma ray telescopes and everything else. Okay. So we have an institute called IUCAA, Inter-University Center for Astronomy and Astrophysics. So the question is, what's the difference between astronomy and astrophysics? Correct. So traditionally, you had these two separation. Astronomers were the guys who are sitting with the telescope. They're making some observations. They're gathering some data, and they're giving that data to the astrophysicists, who are then applying the laws of physics to that data and trying to interpret and analyze and understand what's going on. Okay. So that was the difference. And until about 100 years ago, there was a real difference like this. Okay. Now, in today's context, it's very difficult to make that or continue making that distinction. Because now we have a telescope. For example, in Hanle, in Ladakh, there is a telescope known as the Growth Telescope, which is jointly operated by IIT Bombay and Indian Institute of Astrophysics, Bangalore. That telescope is a completely automated telescope. You just upload what you want it to observe tonight. It will automatically check the weather It will check if it is cloudy or raining. If it's raining, it will just keep shut. It won't implement the order. But the moment the sky is clear, it will open up. The dome will open up by itself. The telescope will start up by itself. It will go on pointing, gathering data, and so on. And it will transmit that data back to the scientists. And so really it has now, I mean, where is the astronomer here, right? The data gathering process has been made fully robotic. So these are called robotic telescopes. And there are literally no humans involved till the data comes. They even have data analysis pipelines. So these people at IIT Bombay, they're looking for transient objects that brighten or fade very quickly. So they have a data processing pipeline. So it observes through the night. And in the morning, when you come in, you have an email stating which are the sources which have changed in brightness the previous night. So you just click on something, you'll get an image and so on. So the whole thing has been completely automated. So, so now this distinction between astronomer and astrophysicist does not exist. However, there are still broadly 3 areas in which people work. And some people work in multiple areas, but most people work in only one area. And those 3 areas are what's called theoretical astrophysics. In the old days, theoretical astrophysics used to be done with pen and paper. But now increasingly theoretical astrophysics means doing some kind of simulation on a computer. Because computers have become so powerful in recent decades that is the way to proceed. And we have sort of reached the limit of what you can do with analytical calculations. So that's one. The second is what are called observational astronomers. These are people who go out to telescopes, they write telescope proposals, they gather their data, they reduce and analyze their data, and then they interpret that data. So that's the second category. And the third category is instrumentation developers. So we have, between IUCAA and NCRA, we have a large team of people working both in theoretical astrophysics as well as in observational astronomy. However, we have very few people working on astronomical instrumentation. And this is a bit of a problematic situation, because if you want to build new telescopes, then the people who are going to build new telescopes and new instruments for those telescopes are the people that we are lacking in this country. So it's a serious challenge. Okay, anyways. So astronomy, it is said, is the last refuge of generalists. So people who just like all of physics, who don't have any specific sub-area, subfield that they're fond of, for them, astronomy is like the dream place, okay? Because in order to do it, okay, various fields of physics are involved, okay? And I've listed some of them, certainly not all of them, and so on. And in order to do astrophysics well, expertise is needed in several branches of physics. Of course, that kind of expertise may be hard to find. You may find it very hard. So somebody who's an expert in plasma physics and also in gravitational wave physics, okay? That may be very difficult to find. So therefore, we have now started grouping together as a community into large collaborations. This is very common in the world of particle physics, where you have hundreds or even thousands of people in one collaboration. Astronomy did not have that until a few decades ago. But now you will find increasingly that there are papers which have 20 authors, 30 authors, 100 authors, and so on. So clearly there are people who have expertise in various subfields of physics that you need to tackle the particular problem at hand. Okay. So you will have to develop this. So you, as a good astrophysicist, you have to think that, okay, I'm an astrophysicist and I'm an expert in relativity, or I'm an expert in Newtonian gravity, or I'm an expert in gravitational wave physics, and so on. Okay, so always have that at the back of your mind. So here's a fundamental cheat sheet for astrophysics. which is every unknown law is a power law. Okay, so if you don't know better, try to fit a power law. Every unknown power law index is plus or minus 0.5, as the case may be. Okay, I mean, if you don't know anything, use that power law index. Every unknown scaling coefficient is 0.1. Okay, so you will frequently see A is equal to KB raised to alpha kind of situations, and this B value will be K value will be 0.1 and the power law index will be 0.5 and so on. And of course, the power law index cannot operate at all values of B because it may blow up. Okay, depending on whether the index is positive or negative, it may blow up at large or small values, which may be unphysical. So it doesn't generally operate. But with this machinery, I think you can do about 80% of astrophysics. This is it. There's nothing more. Of course, the underlying physics of it may be complicated. You may want to figure out why you are getting that particular power law index that you're getting. Power law index is not, of course, 0.5 in all cases. It can be -3, it can be -5, it could be anything else. Okay. So now we will watch a video. Let's see if this works. So this is a movie called Powers of 10. It was made in 1977. And I like to show this movie because it illustrates the scale and size of the universe in just 5 minutes.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider.
So every 10 seconds,
This
they'll
square
go
is
10
10
times
meters wide.
further away.
And in 10 seconds, the next square will be 10 times as wide.
So that's a
Our
10
picture
meter
will center
square.
on the
Now they
pictures,
will draw
even
100
after they've been
meters
lost
square.
to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are soldiers.
They're zooming out from Chicago.
This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet
So
appear
the background stars are not brightening up because they're very far away.
A line extends at the true speed of light.
And
In
now
1
you see
second,
the orbit
half
of the
crosses the
moon.
tilted
That's
orbit
that
of
white
the moon.
ellipse. That bold white line is the orbit of the Earth.
Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun,
The sun.
followed by the massive outer
Those are the
planets,
inner planets.
swinging
and
wide
outer
in their big
planets.
orbits.
Now we are up to 10 raised to 12 meters square.
That outer orbit belongs to Pluto. A fringe of a myriad
10
of
raised to
comets too
13
faint to
meters
see
square
completes
sort
the
of
solar
covers
system.
the entire solar system. We keep zooming out. And now
10 to
we
the
are in
14th.
the interstellar medium.
As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars.
So the sun is only one among the
Looking back
stars.
from here, we note 4 southern constellations, still much as they appear from the
Now
far
we
side of the
begin to
Earth.
see other constellations and so on. Now they will
This square is 10 to the
zoom
16th
out.
meters, 1 light year, not yet out to the next star.
So even the nearest star is
The
not
last 10-second
yet
step
in
took us
the
10 light years
inside the
further.
square.
The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper.
So the constellations are just patterns in the sky. The stars are not at the same distance. Okay, people made those constellations just to familiarize themselves with the night sky. Those constellations, their relative positions remain fixed over large periods of time. So that's why they are stable. Yeah. What was your question exactly? Yes. No, just to show you that the constellations themselves haven't changed. Because those stars in those constellations are so far away that whether you watch them from here or you watch them from Jupiter or you watch them from Pluto or even beyond, they appear the same. They don't change. That's what they wanted to highlight. Okay. So now we are up to 10 raised to 18 meters squares.
Normal,
After
but
this,
quite
things
unfamiliar
begin to
stars
change
and
very
clouds of
rapidly.
gas surround us as we traverse the Milky Way galaxy.
So we are coming out of the Milky Way galaxy now. So you begin to see the spiral arms of the
Giant steps
galaxy.
carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk.
So this is our galaxy. We have left it.
The
Now
two
we
little
begin to see
satellite
other
galaxies of our own are the
galaxies
clouds of
that are in
Magellan,
neighborhood, now up to 10
10 to the
21
22nd power,
meters,
a
22
million light
meters
years.
square. But yet you're not even seeing the
Groups of galaxies bring a new level of structure to the scene.
Now you
Glowing
see
points are no
the
longer
galaxy.
single stars, but whole galaxies of stars seen as one.
So whole galaxies of stars seen as one.
We passed the big Virgo cluster of galaxies
So
among
this
many
is the
others,
Virgo cluster of
100 million light
galaxies.
years out. As we approach the limit of our vision, we pause to start back home.
So what
This
they've done now,
lonely
they've
sea,
gone up to 10
the
raised to
galaxy
24
like
meters.
dust is what
And
most
now
of
they're going
space
to
looks
zoom
like.
in at 5 times the
This
speed.
emptiness is
This
normal.
is about 100
The
million
richness of
light
our
years.
own neighborhood is the exception.
So this is the scale at which the
The trip
universe
back
is
to the
supposed
picnic
to
on the
be
lakefront will be a
isotropic
sped-up
and
version, reducing the
homogeneous.
distance to the Earth's
So
surface
every
by 1 power of
cube
10
in the universe
every
should look
2
more or less the
seconds.
same.
In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity.
So he says,
A rhythm
notice the
will continue all
alternation
the way
between
into our
great
next
activity
goal,
and
a
no
proton in the
activity.
nucleus
Nothing
of
much is
carbon atom
changing.
beneath the skin on the hand of the sleeping man at the picnic.
Now we are in the orbit of the Earth.
10 to the 9th meters,
Moon, and
10
now
to the
the Earth
8th,
becomes visible.
7, 6, 5,
4,
4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter. 10.
Okay. So this movie, you can watch it on YouTube. The link is given there. What it does after this, which I'm not going to go into, is that it zooms into his hand and it goes up to 10 raised to minus 15 meters into the nucleus and so on. So that we will not cover at this time because here we are just doing the astronomical scales. Yeah. So the thing to notice over here in this video is that the universe is a very big place. Okay. The universe is regions of high density are very rare in the universe. Most of the universe is empty or nearly empty. What you would call a laboratory vacuum is what most of the universe is. Hardly any particles. Regions like where we are right now are very special places in the universe. They don't exist everywhere. Therefore, but there are many billions of stars or trillions of stars in the universe. And therefore, There are many planets. There could be even Earth-like planets. There could be life on other planets. All that is there. But it's in a very, very tiny fraction of the ridiculously large volume of the universe. The universe is so unbelievably large that even up to 100 years ago, people were debating whether the galaxies that they saw in the sky, whether they were just gaseous nebulae within our Milky Way galaxy, or they were external galaxies just as big and massive as the Milky Way. And this debate actually happened in California in 1920. And the guys who said, no, these galaxies are not external, but they are within, those guys won the debate. And the reason for that thing was people found it unimaginable to conceive of a universe that was so large. Okay. Let's see now. So when you talk of distances, you often use a unit called light year. That is distance that light travels in a year, okay, which is 9.5 into 10 raised to 12 kilometers approximately. Another unit which is commonly used is called AU, or astronomical unit. This unit is the mean distance between the Earth and the Sun. Okay? And that is about 8.33 light minutes. The nearest star is 4.2 light years away. And the diameter of the Milky Way is 1 lakh light years. Okay? So it is universe, the galaxy itself is so gigantic, it's almost unimaginable. Okay. There is another commonly used distant units in distance unit in astronomy. It's called the parsec. Okay, and the parsec unit is defined as, if you look at this figure, if something, some object or star, let's say, shows a parallax of 1 arc second, okay, that means the distance to the star is 1 parsec. And what is this baseline distance? That's the Earth-Sun distance. So if you see a position of a particular star now, and then the Earth 6 months later will come here, and you look at the position of that star would have appeared to move. That is the parallax. And the angle by which it moves, you quantify it with respect to this, would be P in degrees and P degrees, P arc second in that direction. And if P is 1 arc second, then the distance is 1 parsec. So how much is a parsec in AU units? How will you calculate that? Before you go there, how much is what is 1 arc second? 1/3600th of a degree. That's right. Okay. So your degree is divided into 60 arc minutes, and each arc minute is subdivided into 60 arc seconds. So 1/3600th of a degree is a arc second. It's a very, very small quantity. So if you take, for example, you take a tennis ball and put it on the moon, the angle that it will subtend will be approximately 1 arc second. It's a very small angle. Right. So how will you calculate parsec in AU units?
One parsec times that angle should be 1 degree.
1 parsec times that angle should be 1 AU. Yes, that's correct. That angle should be measured in which units? Radians. So how will you convert arc second to radians, or radians to arc second? Huh? 180 by pi into 3600 will be the number of arc seconds in 1 radian. Okay, so, 1 radian is 180 by pi degrees, right? So if you do that calculation this way, it comes out to about 206265. That's the answer. So 2,06,000 AU is 1 parsec. So, so we can now answer the nearest star is 1.3 parsec away. Okay, if the Earth's sun distance were 1 meter, how far is the nearest star? Sorry, 2.6 or 2.6 lakh meters. Correct. Okay. So how many kilometers is that? Huh? 260 kilometers. So if I draw the sun here, and if I draw the Earth, like let's say 1 meter away, less than then the nearest star is 260 kilometers away. That's how empty the galaxy is. Nearest star, not the farthest. Okay. Now the galactic center is 8 kiloparsec away. So how far is that? So you can take as an approximation that 1 parsec is 200 kilometers away. To simplify the calculation, 1 parsec is 200 kilometers away. So can someone do the calculation? 1 parsec is 200 kilometers. So how much is 8 kiloparsec or 8,000 parsec? 16 lakhs, correct. Okay, so it's 1.6 million kilometers. Does anyone know what is the distance to the moon? Yeah, that's moon. So approximately 4 lakh kilometers. Okay, and this is 16 lakh kilometers. So the center of the galaxy, so this is the sun, this is the Earth. Nearest star we said is 200 kilometers away or 260 kilometers away. The center of our galaxy is 1.6 million kilometers away. It's 4 times the distance to the moon. And that's just the center. And we are not even at the edge of the galaxy. We are sort of halfway to the edge. So the whole galaxy, if you take, will be 3 or 4 times that size. So the galaxy itself is ridiculously large. This explains why that debate happened. People said the galaxy is so big. Okay, how can you imagine other places which are galaxies by themselves? And turned out the universe is a strange place. And the universe is a very big place. So, yeah. So now a table of some distances. So I have said something called luminosity distance at the top. Okay. Do you know what that could possibly mean? You cannot measure you have to measure the distance somehow, yes. But
maybe assume like a certain number of stars in there and then try to us.
Sorry?
You use separate variables for that.
Correct. You use separate variables for the distance, you get the distance and so on. But why is it called a luminosity distance? Correct. So normally you would write luminosity in terms of flux by an equation like this. And you call this as dl square. times the flux. Okay. So a distance defined such that it is luminosity divided by 4 pi times f square root is called the luminosity. So this is just a definition. And why do you think we need such a definition? Why can't we just use the normal definition?
And that's maybe too small.
Parallax is too small. Something else is happening in the universe. For nearby objects, we don't need to specify. Huh? Expansion of the universe is happening. So, and light travel time is finite. I mean, is non-zero, right? So you're not seeing the universe as it is right now. You are seeing the universe as it was in the past. Okay? So it's very hard to define a distance because the light, when it has left, there is nothing there right now. That galaxy has expanded. It may have even died out or faded away. Anything could have happened if it is billions of light years away.
We measure L.
Huh?
Flux we can measure directly.
L you can measure. So for example, if you measure Cepheid variables, then there is a calibration that is available between the period of the Cepheid variable and its luminosity. So measuring L is a complicated business, but there are ways in which you can measure.
L would be the luminosity of the Cepheid variable and flux is the entire galaxy.
No. The distance would come from the Cepheid variables. The luminosity would come from this definition of the L. I'll come to that. We are going to cover all of those things. Okay. So the Andromeda, so now you will have, just like you had parsec, now you will have kiloparsec and megaparsec and gigaparsec and so on. So the nearest big galaxy to us is the Andromeda galaxy, and that is 700 kiloparsecs away. Okay. So for scale, the Milky Way is about 30 kiloparsecs in diameter. And this is 780. So it is not ridiculously far away, right? If you can imagine the Milky Way like this in some units, so that is up to say 20 times further away. So if you make the Milky Way with a diameter of let's say 1 meter, then at the end of that room, Andromeda will be sitting. The Virgo cluster is 16.5 megaparsecs away. So Andromeda is less than a megaparsec. So it is 16 times further away. But even that is not unimaginable. I have a 1 meter Milky Way galaxy, and at the end of the room, I have Andromeda, and maybe 20 times further away, other end of NCRA or something, you will have the Virgo cluster. The Coma cluster, so these are clusters of galaxies. We will cover those. This is Virgo is the nearest reasonably large cluster. The nearest really big cluster is the Coma cluster with more than 1,000 galaxies. And that is about 100 megaparsec. So even that is not unimaginably large. The nearest quasar, which is an object known as 3C273. 3C stands for the third Cambridge catalog. And that object is about 750 megaparsecs away. And farthest known galaxy, okay, this is a slightly moving target. This is as of a few months ago. GN stands for galaxy something, and Z11 means it has a redshift of 11 approximately, and that is about 32 gigaparsecs away. Now, as higher and higher redshifts galaxies are found, they're 12, 13, 14, etc. This distance may increase, but not very dramatic. So if you see what is the sort of the size of the observable universe, that has a radius of about 30, 40 gigaparsecs of that order. Why is the size of the observable universe finite? Sorry?
The speed of light is
Because the speed of light is finite, and what else is finite? Age of the universe is finite. Okay? Because the speed of light is finite and the age of universe is finite, the size of the observable universe is finite. The universes are today about 13.7 billion years old. So you cannot see objects that are whose light has taken more than 13.7 billion years to reach you. Does that mean that the universe itself is finite? No. So there could be objects, galaxies, people, everything in parts of the universe that is not observable at the present time. And every day that passes, one more light day of radius is available to you in the observable universe. Right. Okay. So this parallax idea is more than 200 years old. Okay. However, there are limitations on the parallaxes that you can measure with old technology. So 100 years ago, if you went and told astronomers, I want you to go and measure the parallax of this star, first of all, they'll take minimum of 6 months to measure the parallax. And when they come to you, they will often have such large uncertainties that the parallax measurement will not be very reliable. So they could, with a lot of effort, they could go up to about 10 parsecs. Now, I forgot to mention here, a parsec is approximately 3.26 light years. Okay. So if you go to 10 parsecs, then you're going to about 35 light years. And there are only maybe about a dozen or a few dozen stars that are within that distance. So they measured the distances to these stars. And then they obtained some indirect calibrations and so on to estimate the size of our galaxy. Okay. However, it was only with the advent of the Hipparcos satellite that we were able to measure parallaxes for many more stars, because we could achieve an astrometric precision of about 1 milliarc second. 1 milliarc second means you can observe, reliably detect, measure distances up to 1000 parsecs. That's about 3000 light years. Now, there is a next generation version of Hipparcos, which is called Gaia. It launched in 2013. It is intended to measure 1 billion stellar distances to within 20 microarc seconds. So we went from 1 milliarc second to 20 microarc seconds. So that is like a 50-fold improvement in astrometric accuracy, which means we can measure parallaxes 50 times further. The errors in measurements as far as the galactic center were about 10%. So this Gaia telescope has been really revolutionary in the measurement of distances. And this is really very important, because what you want to do, we'll come to that probably in the next lecture, is that what you want to do ideally is that you want to construct what is called as a distance ladder, which means you want to measure distances to nearby objects, calibrate that properly, verify it, and then measure the distance to the next furthest objects in units of this distance. So once you know that, okay, this particular star is so many parsecs away, you can leverage that information, probably indirectly, for example, using the Cepheid variable technique. You calibrate it, and then you say, okay, that particular star is also a Cepheid variable, and it has a certain period, and therefore its luminosity should be so much, and therefore its luminosity distance must be so much. I can measure the flux. Okay. So using that formula, one can find out the luminosity distance of these objects. And you keep on doing this. You keep on doing this, climbing up the cosmic ladder. And there are various objects that come to your aid. Cepheid variables are relatively useful to measure relatively nearby distances. Much further distances you can measure using what are called type 1a supernovae. Okay? And you can measure the size of the entire universe. And this, of course, is very important in cosmology because cosmologists need to know the size of the universe at any given point in time in order to determine how the universe evolved on the largest scales and how it is going to evolve in the future. Okay, so I think we can stop here, and if there are any questions, we can take them, and we'll continue next time, which is on Thursday. You don't really require to be an engineer. So for example, I mean, it helps, but your training can be in physics also. But having a slight engineering mindset helps, because to build an instrument requires a lot of patience and a lot of skills in engineering also. So for example, Ram Prakash, who's a big instrumentation developer in IUCAA, Ram has a degree in engineering, and but when he did his PhD, he did it in physics. Although he did it using instrumentation, he built an instrument during his PhD. So it requires you to think in two different ways. It requires you to think like an engineer, but it also requires you to think like a scientist, because you don't want to build an instrument that is not really serving the requirements of the astronomer. So you should have an astronomer's brain, and you should also have an instrumentation developer's brain. It's very difficult. And I think the reason we are not developing enough instrumentation people in India is because we in our education system, experiment is not given much importance because the labs are difficult to set up and maintain, they're expensive and so on. So everybody wants to do sort of pen and paper kind of work. And that has led to this unfortunate situation. And we are now participating in large projects. So we are participants in the 30-meter telescope, but NCRA and others are participants in the square kilometer array project. That's a real engineering project. And without engineering, it can't be built. And we are finding it difficult to find people within the astronomy organizations. So we are going out, so we are building mostly software for the monitoring and control system of the telescope. So that software is being built by industry partners. So we have to go to software industry people, big companies, and they help us design and build that software. So, but hopefully now, because of this startup industries and so on, there will be tie-ups with private companies also. So we, in the SK context also, we are starting to build some of the feeds for the SK observatory. And those have been designed by engineers. And they will be built by the engineering companies. They will not be built by ourselves. So outside of academia, there is a lot of connection and interaction with industry. Any of you have an engineering background? Probably not. You do. Okay. What kind of engineering? Yeah. Okay. So we will stop and